Okay, we're gonna move on now, and we just had Brian Holmhansen arrive. This is Dr. Holmhansen. He's the ONR program officer that funded this entire program. So anyway, welcome.
Thanks very much.
Yeah.
Thanks very much.
And he planned to be here this morning, but his flight was canceled last night due to weather out of Dayton. So anyway, I'm glad that you pushed through and found another flight that could be here at least for this afternoon. So
Thank you. Yeah.
So we've got, so we just wrapped up basically the analysis side of this airplane and the control and everything, the aerodynamics and control. Ben is going to take about 30 minutes and go over the flight testing that we've done up to this point. And then before we go flight test, we're actually going to take an hour and go over this work for the buyer that we've been doing with the Air Force and introduce you to that. So yeah, I'll turn the time over to Ben.
Okay. Alrighty.
On time. Good.
So I'm just gonna, I do have a presentation I want to pull up just one moment, sorry. So I'm gonna talk a little bit about the flight testing and some of the things we've learned along the way. And a lot of this will be me pulling up these slides and then going back and watching a video, and then we'll go watch another couple minutes of video. We won't be watching all of the footage. So we've done, oh golly, let's see, we've done 8 flights, 7 powered flights, 1 glide test. And so right here, we've got a simplified breakdown of each flight and the purpose as well as the result, how well we were able to hit those purposes. So the first thing, back in April of last year, we did a glide test. So we launched the aircraft, and I'm gonna pull up the video of that since that one's pretty short. And once again, these are all on the lab website. So a couple things to learn from this flight. First thing, we learned that the airframe was statically stable longitudinally and laterally. That was a really, we didn't know. We designed this aircraft fully using numerical lifting line, and so that was one of our big first steps. We wanted to know that whether it was stable. So you may have noticed that we launched it using a bungee. So I'll go back to the beginning, and this was definitely one of the bigger. I would say there's at least 3 or 4 big things that we learned throughout the flight testing process, and one of them was how do we launch this airframe? It started out as I think 18 pounds, and it's slowly gained weight till it's almost 23 pounds. And so I think that was one of the big hurdles that we had to come across was how do we launch this airframe? So we have a bungee attached to a hook on the underside of the leading edge of the center section. You can actually see it on this airframe, and that's gone through a couple of design changes as well. But that's how that is launched. And so you can see we originally started out with 1 person holding each wingtip, letting go, and that has improved. and we'll go into that a little bit more detail.
Was that controlled or was that open loop kind of free flight?
I believe it was
open
controlled.
Loop.
I believe we had someone on the transmitter.
Well, yeah.
But I don't think he
But that's-
touched anything.
But that's open loop. So if there's no feedback to the
I see.
automatic feedback to the controller. Yeah.
Uh,
Yeah. And by the way, everything that we're doing is open loop. On even today, what we'll be flying is open loop. So,
The open loop in the sense the pilot's closing,
yeah, yeah,
directly commanding
yeah,
control surface deflection.
yeah. But we won't be in any autopilot mode where, where the,
I was wondering if this one it was launched to some initial velocity and that was just totally
oh, I
no
see.
surface movements at all. That was the free.
Was mostly, yeah, he did control it a little bit, but yeah.
Because I was trying to think, okay, there's a little bit of
oscillation in
dynamic
there.
in there.
Yeah.
If that was from the
Yeah,
human or the,
and we'll see more Dutch roll, you know, obviously with the swept wing aircraft.
Yeah.
Dutch roll, so we'll see that in some later videos too.
So the two purposes of that flight were to test static stability and the CG location, making sure that we were about on the money for where our CG was located, and we were able to meet those purposes, so we considered that flight test successful. Our next powered flight was a couple weeks later. So we've been going through some structural design changes. Long story short, I made some holes in the spar and we realized that was not a good idea. And so the next flight, so May 3rd, 2021, that was the next flight, fully 3D printed airframe. However, we didn't have those carbon fiber spars inside of there. And so it was fully 3D printed, 100% plastic, excluding electronics. And so the purpose of that was to test the structure, see if it could actually support the loads that we would experience in flight. It was also to test the mode 1 that Zach was talking about. So all the control surfaces were elevons. They had only roll and pitch command from the pilot, as well as testing our propulsion system and seeing whether we were able to provide enough power for a flight. And so we'll watch a little bit of that one.
did you do any like static load testing to estimate the stiffness of the wings before going to?
We did. We did back near the beginning. We had pulled out sandbags and we would put like, we calculated the lift distribution that it would expect in flight, and I believe we tested it out to about 4 Gs. And so we would put little sandbags on each section, and it passed that test. But the stiffness was the biggest problem. And this is where I'm a little uncertain, even, but the stiffness was a problem, and that's what we discovered in this flight, was that the wing could support that 4G loading, but that 4G loading limit wasn't good enough for our flight expectations.
Yeah, okay, so that was like that subtle difference between when you load it up, there's like a loads test to say, can you take the load versus how much does it deflect for like a stiffness evaluation to see is it stiff enough, which is usually, I'm sorry.
Oh, no,
But usually that's the challenge, because you can design something and say, yeah, this will handle our loads. But then when the aeroelastic folks come on board, they'll say, well, you know, that has to be stiffer, and the structure gets heavier. And anyway.
And that's exactly what happens. So we'll see it, but basically the stiffness started interacting with and this is definitely not my area of expertise, but the stiffness started interacting with the short period mode in the aircraft, and I believe that's called body freedom flutter. Is that correct? But we'll watch that. So watch the launch. So once again, 2 people holding the aircraft, bungee onto a hook on the bottom of the aircraft. You can hear the ducted fans in there. See if I can get over a little bit. And once again, this was one of the problems that we noticed. Us 2 people letting go at the same time, it's really hard to coordinate that. So it launched, and we'll get into how we improved upon that launch later.
Usually we cheer joy after landing.
Any little thing. Any little celebration was no.
You see that right there?
Right there.
That's a good
That's
spot.
what I wanted to pull up. You can see this tally of the airframe.
It's like body freedom flutter.
And we've been having problems with the center control surface. And so during this flight, and I believe the next at least 2 or 3 flights, we had that whole control surface taped up. He wasn't able to control that base section at all. It was purely the wings. You can see the flutter a little bit there, or the body freedom flutter.
Do you have aeroelastic analysis for the flutter?
No, do any air elastic stuff. So you'll see right here, this was a key moment.
There you go.
Right there.
Yeah. That's what E to the positive number times T.
That's what it gets you. Yep. We learned that Horizon doesn't want to clap its hands. Once again, we were able to test out the propulsion system, able to test out mode 1, everything looked good. The pilot did notice some, he called it spooky behavior. He noticed some problems in the communication, and we'll talk about that here in a minute. But the structural design was definitely a problem. And so at this point is when we went back to the drawing board and put these carbon fiber rods in. So there's carbon fiber rods. They don't have that section right now. Correct. I'll show it to you. So there's these holes in the upper and lower web of the spar.
Mhm.
And so these holes, we slide these carbon fiber rods through covered in epoxy to help maintain the structure throughout the wing. And so that's the design change that happened in between powered flights 1 and 2. And so moving on to powered flight number 2, so that was about 2 months later. We'd improved on the structural design. We wanted to test out mode 1 again, once again, because the pilot had felt a little bit of that, what he calls spooky behavior. And we, more than anything, wanted to make sure that he was able to fly this airframe and bring it back down in one piece. And we also made a change to the electronics setup. Due to some input from the pilot, he suggested some changes that we make to the electronics distribution. And earlier, people may remember that I talked about how the airframe has 3 different circuits. One, basically, it breaks down into one controls the wing, one controls the other wing, and the servo section, or the center section, excuse me. And the motors are attached to each of those circuits. And then a third circuit controls mostly the electronics. So the electronics inside there, the cameras, Pixhawk, receiver, the controller board, all those things are controlled in that circuit. So it wasn't quite towards the final design, but we got a lot closer on the electronics setup for this power flight too. So we'll watch just a minute of that.
Can I ask a quick question for the carbon fiber rods? I'm assuming that the main thing was to get more stiffness into the wing, right? So was there a specific type of analysis to say that's going to get you the stiffness you need, or you need 4 rods on top, 4 on bottom?
No. So we just started off with the idea of having 4 rods on top, 4 rods on bottom, and then we changed the way we were doing our load testing. Originally, we were doing the sandbags, but then we decided we'd do a wingtip test. So one person stands on one wingtip, one person stands on the other. And that was the big reason for this power number 2 flight. It was able to pass this wingtip test. And I don't believe, and this is where I'm uncertain, I don't believe we've done that wingtip test before. So I don't know whether previous airframes have passed that test. But that was the purpose of that second power flight, was to see if we solved that stiffness problem.
So somebody was standing on the wingtip? Did I hear that?
No, sorry. One person holds the wingtip and we pick up the aircraft.
Oh, okay.
Fully loaded with batteries and such,
Okay.
to make sure that it's able to take that bending. But once again, I don't think that quite answers your question. We didn't do any air elasticity analysis or anything.
But it's a interesting solution, and probably some good additional research on kind of like you got carbon inside a 3D printed structure. There's probably some interesting ways to look at that and see how that, because you probably didn't add any weight to the structure with the carbon, right?
No,
Maybe you reduced it.
Yeah.
So you solved the flutter issue without adding structure, which is, people like you might want to hear about that.
I mean, all the airplanes are pure carbon fiber anyway, right?
Yeah.
This is just some testing on the field. Okay, so here we're still having 2 people hold the aircraft. So this is a slowed down launch, and you can see because there's 2 people, it's just hard to coordinate that, and especially we can usually give it a little bit of a pitch up or a little bit of a roll. Thankfully, the pilot was able to correct for that. So there's that launch. I'll skip forward. You can see that nice lean camera there. I believe this was the first flight that we had cameras on board. You can see this jittery behavior, and this was the flight where we started noticing this. This is another huge problem that we had to overcome. We had to figure out why. Originally, we had.
Would you just silence the video?
Yeah. Originally, we had this, and maybe I'll pause for just a second so I can talk about it. Originally, we had, it's called a Dragon Link. It was more or less something that plugs into the spectrum. So this is the transmitter, and it would plug into this transmitter, and we would be able to transmit through the transmitter, but it would go through this, it was called a master transmitter. So, and once again, this is, I'm a little fuzzy on it, but we noticed several problems with it, but we did it because it would transmit a signal in a certain way so that the aircraft, we would be able to split off this signal and command 11 control surfaces. So that signal system was called PPM, pulse position modulation. And we were just getting, and once again, the pilot would call it spooky behavior. It would do things that he didn't command, and it would kind of concern him. It would kind of concern him. So on this flight, that's how we had our transmitter set up, and we're noticing this jittery behavior. And we saw it before. I'm going to see if I can get another example of it.
There you go.
I'll skip forward to the end. There you can see that jittery, and I don't believe we have the pilot's voice on here, but up about right here, he's saying, you know, I don't have it anymore. For some reason, control system completely gone, and the aircraft just nosed into the ground.
Okay, here's some Dutch roll right here. There you go. So he puts some roll input and then he just lets go. You're just trying to see what the Dutch roll look like. So you can see that's all for your
There's that
response.
jitter right there. There's that jitter. I'd never noticed that inboard control surface never moves. I wonder if it was a dead servo. That's interesting. So we lost that airframe. I don't think there's much else to talk about that one. So obviously we had a problem. So that was powered flight 2. I'll go briefly over powered flight 3. Long story short,
Troy knows how to fix it.
okay, thanks, Troy. We were able to fix some of the problems with the center conformal flap, and so we wanted to test it. Once again, before this flight, we had it taped close so it couldn't do anything. We also wanted to make sure we could get data on the Pix Hawk. I believe that powered flight number 3 was the first flight where we had the Pix Hawk, and we also wanted to test mode 2 and see what ranges the pilot would command to see how that would fit within the control methodology. And you can see the result. It crashed on takeoff. Let's see. I'll just show that real quick. We'll go here.
Straight to the punchline.
Yeah. So once again, we're still holding the aircraft. It's painful to watch this. Well, it's not so painful because I know we solved it, but it's still. Okay,
Why did it bank so hard? You know what happened?
that is a good question, and it's going to take me a minute to try to remember. I believe what we thought happened was that it didn't have enough launch energy, and so that started going, but it didn't get enough energy to start going up to cruise like he needed. And from what I understand, we talked about, we came down to believing that it stalled right on takeoff, and he just couldn't control it anymore and lost it.
Yeah.
Do you have any input on that?
Yeah, we think it was just a stall. So the aircraft, I think it gained some weight, and yet we pulled the bungee back to the same amount that we had been
Oh,
for
okay.
previous flights. And so it didn't get enough momentum, and it was pretty kind of abrupt pull. I think if you go back and watch it, and we've poured over these videos, but I think right as it came off, it was at a really high angle of attack.
Mhm.
And so here, go back to right as you release it.
It looked like the AOA got really high at the.
Yeah. So right here, is this the quarter speed? We need a slow motion one
Okay.
to see. Here we go. Yeah. Okay, so here we go. Let that go. Okay, so look at the angle of attack. Do you see that?
Yeah, it's pretty high.
Yeah, so that's a whole bunch of drag, and it just couldn't get the momentum up. Now it's finally getting momentum.
Looks like it got helped by ground effect. On that.
Yeah. And then it gets off here, and then again,
There it
really high
goes.
angle of top. I
Yeah.
mean, you can't pull out of that. The motors are not strong enough. And so here we're just, so it's not stalled here, but now the motors are at such low speed and the aircraft's at such low speed, it can't get its momentum up.
Yeah,
So now it's just gonna stall and
yeah.
crash. So it was just a launch, and that's what we fixed. I think that's probably the next thing we're fixing here is our launch mechanism. It was just really unpredictable. So we came up with a better way to launch.
Okay, so just like Dr. Hunsaker said, that was the next step, was solving that launching methodology. And so you can see on the next one, we were trying to test this new launch setup. So with this new launch setup, instead of having one bungee, we had two bungees, and then we had a paracord attached to that bungee that went back and attached to the aircraft. The idea being that it transfers twice the amount of energy in about the same amount of time. Through some calculations that we've done, we determined that it should be enough energy to get the aircraft going. Let's see, what else on this flight? We once again wanted to test that center flap, and wanted to make sure that we were getting Pixhawk data and test out mode 2. So this flight,
Let's skip this one.
okay, I'm fine.
So we had another loss of signal issue on this, and then so that was in November. We spent the next 5 months pouring over our electronics, because that has caused 2 of our crashes, a loss of signal while and so we finally narrowed it down to the Dragon Link that we were using, and so we got rid of the Dragon Link, and so that got us onto this next one, and this was just in April.
So we changed the setup of the receiver, got rid of the Dragon Link, and so we were testing those same things that we talked about earlier. And I'll just do a couple seconds of this flight. We don't run it everything. And I'll show. So we did some bench testing. Well, some testing on the ground to show. Okay, so here's our launch. So we launch on a table. Someone cuts, Zach cuts the paracord with scissors. You can see that launch was a lot cleaner than the other ones that we had. Getting rid of the human variable certainly helped. So I'll skip past this part a little bit. Let's see. Trying to remember what we're looking for on this slide. Oh, okay, that's right. So this was our first time ever testing mode 2 in the air. And I believe it's right around here. I apologize, just 1 minute. There we go. This is it. So he switches over to mode 2 and he gets this big pitch up maneuver. And you can see it causes a bank. And this is the thing I wanted to point out. That center section stays up, even though he's commanding it, you can watch it, that center section stays up, and so it's just dumping lift this whole flight. And so it's in this glided stall, and he's trying to pull out of it, and so we call this our first attempted landing. Because it wasn't quite as bad.
So did that lose signal or the servo got stuck? What happened?
That's a good question. I believe that the servo got stuck. I don't think it was a signal problem. Part of the problem was we were using a servo. I designed it so that it was a servo that wasn't powerful enough. We needed it to be able to do plus and minus 20 degrees. and it just wasn't powerful enough to do that. And so I think, and the bigger part of the problem was it was using a 3D printed arm. So these servos, they work on a little gear shaft, and it's got this arm on this gear shaft. And we didn't have an arm long enough to control this control surface because it's got such a large aspect ratio. And so, sorry, I lost my train of thought. And so I believe what that initial roll maneuver did is it broke that arm, and so it got stuck in a position that it just forced that control surface to be up.
Yeah.
So because of that, we changed the design of the control surface or of the servo in there. And I believe that's everything, and that you can see our flight path. Okay, I'm gonna skip this one for time reasons, but basically we realized that we had been using, we originally cut it with scissors, but then we decided, you know what if we had this quick release mechanism? So we had a quick release mechanism that you pull a string, let's go, and you have this metal ring on the end, and this metal ring hit the bottom of the table, goes over and whacks the aircraft, and among other things, it caused the wing to snap in flight. Yeah, it's short. I'll just show it quick. Right there. So it comes over. Let me get this a little bit bigger. You can see. Oh, excuse me. It may have already happened. No, there's everything. It already went around. So there it is. It goes around the airframe. Smacks on the other side of the wing, and we believe this was actually because there wasn't enough epoxy on those carbon fiber rods. I don't know whether it was affected by this. There may have been two problems that happened simultaneously, but anywho, so you see that wing snaps and it starts to roll.
Oh, it actually damaged the wing.
Yeah.
Wow.
Good thing we don't do that anymore. Okay, so moving on to our final flight. Sorry, I'm running out of time a little bit. So our final flight, we wanted to make sure we had a clean launch, no drops in communication. We wanted to test mode 2, and we wanted to have a purposeful landing.
That result is not correct. That's successful. We copied that from another.
Oh, I apologize. That is correct. That is correct, but that is not correct. That was a successful, sorry, that was a successful flight. Edit that right now.
Loss of signal was fake news.
That's the default.
Honestly, we had so many flights that was the default. Okay. So this launch, we went back to the scissors. Aircraft's on the table with a ring attached to a hook on the bottom of the airframe, and then we just cut that string, that paracord with scissors. Let's see. Oops. Okay, so we cut it. Launches beautifully. We got pretty close to hitting the stakes, if I recall.
Oh, yeah.
Right here. So this was a wonderful flight. Unfortunately, it's kind of boring to watch.
What you mean, fortunately?
Fortunately, I guess, yeah. So I'll skip forward a little bit to the landing. So we were able to test mode 2 for about 2 minutes, I believe. And I believe he just pulled out of mode 2. He's in mode 1, so he's in the safety mode. He's getting ready to land. And he's coming back around, and I'll just let this play out.
You can turn on the audio. We've got the pilot mic so you can hear.
That's the end of my base, very crossword. Oh, geez.
Very enthusiastic.
Sorry about the breakup. That was beautiful.
So we consider that a successful flight.
I felt,
Seems like there's something about the, what's the right word, like brittleness of 3D printed structures that held pretty well in flight, but one impact and I don't seem to have like, right? Yeah, the toughness to impact.
So that's the flights up till now. That was on this Monday. So today we'll be testing out a couple of the changes we've made and hopefully we'll be able to test mode 4.
Did that one didn't have the rods in it, I'm guessing, the one that you just showed? Or did
It
it?
did.
It did have the carbon.
Yeah.
Shaded right through. Wow.
So, yeah, so today, so in an hour, actually, we're gonna leave and go out to the flight test field. We're gonna be flying this guy and it'll be the first time that we're testing mode 4. Mode 4 is our mode that controls yaw. Up to this time, we've only been controlling roll and pitch. But this will be the first time that the pilot is handed a yaw controller, and so we have a plan for that flight. Anyway, we only have about 4 to 5 minutes in the air on these batteries for this aircraft. And so we have to use our time really wisely. So anyway, we've got a plan for it, but it will be a true flight test. This is not a demonstration. This is another flight test. So this is the real deal. So
All the excitement.
yeah, with all the excitement. So
It's a good word for it.
anyway,
So
So,
the
yeah.
way for yaw effector, are you using kind of crow's foot?
yeah, actually, let me pull this up.